I hope you're still doing well. We are going to talk about vertical circles, and vertical circles deal with things like loop-to-loop roller coasters, as you can see in the picture here on the screen. We are going to start off, though, reviewing elevators. If you remember elevators, it was something I said we would come back to later in the year, and here we are. When a person is on an elevator, their weight is pulling them downward, and there is a tension on a string which is pulling upward. And depending on the acceleration they're experiencing, there is a greater upward tension than downward force of their weight. And so what happens is the floor, thus the scale, has to push up on them, so their apparent weight appears to increase. And so we say in the equation that the normal force plus the weight has to equal the net force. And so we end up saying with that the apparent weight is going to equal that net force, the normal force, the normal force. And so the normal force is equal to the net force minus the weight. And so we see that when they are accelerating upward, they have a greater apparent weight. When they're accelerating downward, they have a smaller apparent weight. When they are moving at a constant velocity, up, down, or not moving at all, their apparent weight and their actual weight are going to be the same. Keep that in mind when we move into vertical circles here. So we're going to do some derivations of equations. There are two places we're going to look at. We're going to look at the top of the curve when we're at the top way up here, and we're going to look at the bottom. And these two locations are going to have two different equations to describe what is going on, but ultimately it's going to come back to this general equation and the signs of up and down. So when we look at a object traveling in a circle, as I was saying to you, you have, if the train car is at the top, and you are under, we're going to look at it specifically as the train car being under the circle, with the person's head pointed down to the ground, as it would be in a loop-to-loop. It's a little bit different. It's going to have a different sign when you're going over top of a curve. So if you have a car going over a curve like this, that's going to have a slightly different equation. Sign difference, same equation we're about to see, but just sign differences. But we're going to look specifically today at the roller coaster scenario, top and bottom. So when we're at the top of the roller coaster, we have our weight pulling down. Gravity's like a bad friend, always pulling us down. And we have the track itself that's pushing down. And the reason the track is pushing down is because as the train car is going around the curve, when it gets here, an object in motion is going to want to stay in motion, and it's going to cause something has to be pushing down on, and that's the track itself that's going to keep you in that circular path. And so those two things added together are what we ultimately call our centripetal force. The centripetal force is going to be the sum of those two things. And so at the top, the centripetal force is going to equal the weight downward plus the normal force downward. Or in other words, what we find is that mv squared over r is going to equal mg plus the normal force. And that normal force is going to be what your apparent weight is going to be equal to. So we do a little bit of solving here, and if we can solve for velocity, we can multiply both sides by r and divide by m, and we can get the velocity at that you would be going to have a very specific apparent weight. The normal force is that apparent weight. But in a dramatic roller coaster ride, the objective would be that you get as close to weightless as possible. And so if we want to see the minimum speed you could go without traveling around the curve and falling inward, we would set this value to 0. And when we do that, we end up getting mv squared over r is equal to mg. And so the m's cancel out, and we get a very simple equation, which is v is equal to the square root of gr. This equation here describes the minimum velocity that a person needs to go in to stay in the circle and not fall inward. So if you've ever seen one of those little Matchbox cars or Hot Wheels cars that goes around a ramp and seems to stay on the ramp, or a marble that rolls down a ramp and seems to stay on the ramp without anything holding it there, it is because the outward inertia of the object is going to keep it in its path while the normal force of the track is pushing downward. And as long as it's going faster than this velocity here that is solved by the square root of gr, it's going to stay in that path. If it goes slower than that velocity, if this is the track, all of a sudden it falls inward. So if you're going fast enough, it's going to stay right in the track. So that is what happens at the top. At the bottom, I'm going to do another drawing here. So I'm going to draw the loop again. And at the bottom, what we're going to see is that we still have mg pointed down, but in this case, the normal force is pushing up, and that centripetal force is towards the center of the circle. So that centripetal force is also going to be pushing upward at this point. Right here, I'll draw it in here. Right here, there's your centripetal force. So the centripetal force, say we start off with the same equation we did previously. Centripetal force is equal to the normal force minus the weight this time, because they are going to be in opposite directions. Normal force is down and the weight is up. That means that when we solve this particular equation, that we get that mv squared over r equaling the normal force minus mg. We bring mg over to the other side, and now we get the normal force is equal to mv squared over r plus mg. This is important because this is what your apparent weight feels like at the bottom of the roller coaster. You go around that loop, and when you get to the bottom, the track itself has to be pushing up on you with a force greater than your weight. Otherwise, you're going to slam into the ground. Just like an elevator, as you're moving downward at a constant speed, all of a sudden needs to push up on you to create a greater upward force than downward force to cause the acceleration to decrease your downward velocity. And so in this case, if you were to put a scale under your butt as you're going around that curve, when you get to the bottom, you are going to appear to weigh more than you did when you were just sitting on the ground. At the top of the loop, we said that normal force was going to zero. Now, if you are going faster, this is a very interesting fact. If you were going faster than the minimum speed we talked about, now your apparent weight goes from zero up towards your actual weight. And if you're going fast enough at the top, you can actually have a greater apparent weight at the top than you would just sitting on the ground. But you have to be going very fast at that point. And then when you come back out at the bottom, you would have an even greater apparent weight. This idea of increased weight is called G-force. And when we're talking about G-force, what we're talking about is the idea that there is some multiple of gravity. So if you say that your true weight is equal to 200 newtons and your apparent weight is equal to 400 newtons, what we would say is that this would be 400 divided by 200. So you are two times as heavy, and so that would be described as having twice the gravitational pull, or 2 G's. Another way of looking at this is just purely on acceleration, because if your let's say your acceleration was 19.6 meters per second squared. That is 19.6 divided by 9.8 meters per second squared. That's 2 times again. And so again, you would have 2 g's. G just says that it's 2 times whatever the normal value was at 9.8 meters per second squared. And so in a person traveling around a circle can experience 3 and 4 g's in a normal roller coaster ride, a normal amusement park ride. As we approach 5Gs, we get to something called blackout, where the blood can start to move out of your head into your feet, and you literally pass out. If you were to flip over on this curve, you could actually, and you were going on the top of the curve instead of the bottom of the curve, in terms of the loop, you actually could have the blood accelerate to your head, and that's called a redout. So you could have redouts and blackouts depending on which way your body's positioned. And so as we are looking at the problems, you may see some of those terms. Hope you have a great day. If you have any questions, please don't hesitate to ask.